Okay, good morning. I'm Charles Poe. I'm one of the lead developer in computational geometry at Wolfram Research. Today I want to talk about constructive solid geometry in the coming version 13 of the Wolfram language. So what's constructive solid geometry? So essentially it's a technique, a scheme of representing solid, right? Let's just think about 3D solid. Right, has Boolean constructions, a combination of Boolean object where you have some base primitive like cylinder, balls, and then you combine them, intersect them, or make union or difference, right? And you hope that those operations stay. Those operations are set of regularized operations. Essentially, you hope or you want them to always generate a solid object. Right, you don't want to intersect two cube, which just for example on the face, and you don't want to actually have a plane. So what you actually want is a solid. So is what we mean by regularized operation. So I will come back a little bit more in detail on that later on. So one key advantage of having a CSG representation is that you can look at it as an order binary tree. So, you have a picture here, pretty much. So the non-terminal node represents the transformation. So, rotation, translation. And in principle, what you want to do is to stay within a rigid transformation. Because in this case of solid geometry, you want to actually, preserve that physical fidelity. You don't want some arbitrary transformation. So the non-terminal node have the transformations, which are generally affine transformation, rotation, translation, and such. And they also have the regularized operation, intersection, union, or difference. Right? And the terminal node have a set of, leaf primitive, right? So as I say, disk, ball, cylinder, and such when you're in 3D. And in 2D, you can have a disk or polygons. And when you combine all those operations, you can actually construct really complex objects, right? And one key advantage of actually, going to that direction of, doing modeling with constructive solid geometry is that it can capture the design intent when you want to actually add or remove object, right? So if, at the beginning you have a cube and then you want, for example, to, build a hole in between in that cube, essentially a void, you can actually just take a cylinder and then just run to it. So you make a difference with that cube and then you get the object. So through the specification or the description, right, you can actually capture that design intent. And one advantage with that is that it's concise, right? You can just say, remove, right? Difference, kind of give you that concise description of your object. And also it guarantees the validity of the solid, right? Because we want to operate on solid. We want to intersect them. You want at the end to still have a solid. We don't want lower dimension, point, or line, or plane, right? And one key advantage is that, after that modeling or that description of your object, you can just, transform it to Boolean, operation. Describe it as, a Boolean algebra expression, right? And that's kind of give you that computational aspect of that. And in this talk, I won't actually focus on that computational aspect in terms of, how to compute the volume on such, just keep in mind that it's just, you have, solid object, you can just represent it as a Boolean region or such and then compute on it. Right? So the other property is that, it gives you a natural control, right, in terms of parameterization of your, scene or your object, right? So for example, if you have a ball, you can easily change the radius and then you will change your model, right? So that's kind of one of the powerful property of, this scheme or technique of modeling. So now, how do you do that in the Wolfram language? So in version 13, we introduce an object we call CSG, CSG regions. So you take a first argument where you have the function, and then the second argument contain a list of regions, right? And this region can be nested CSG regions. Right? So this is an example where essentially you take a cylinder and then you make a union of those two cylinders, three cylinders essentially. I take the original cylinder, I rotate it, pretty much align it with the y-axis, the x-axis, the next one with the y-axis, and then I do a union, and then I get this object. So the key idea with this modeling technique is that you can easily, as I said before, add or remove from it, right? So now if we look at the list of operations, right? So one operator is intersections. So you can intersect two solid objects. So at the end, what you get is a solid object, or you end up with an empty set. You can intersect two, you can make a difference of two solid objects. So you also obtain at the end a solid object or an empty set, or you can join two solid objects, so union, and at the end you end up with a solid object. So all of those are in quote regularized operations. So you make sure you don't have low dimension object, no plane, no point and such. So this example just show you the result of those operations. We just resize this. So this is the intersection of three cylinders. Actually, I have two cylinders here, sorry. So you have the result in here. This is the difference, and this is the union of the two cylinders. So you see that you can easily capture, the intent of your design. You want to join them, you want to make a difference and such, right? And so also this is kind of, also we try to preserve, our generality is to, cover all dimensions. So in our approach for design of geometry. So our CGS region, work on 2 dimension, 3 dimension, and we hope to actually push it to n dimension, where you can actually design your object just based on those Boolean operations. So these are the set of primitives we support at this time. Disk, ellipsoid, simplex, essentially triangles, and stadium shape, right? And you can imagine if you support already simplexes, so that pretty much means you can actually cover the case of boundary mesh region and such from this description, because boundary mesh region or mesh region essentially a union of triangle of simplexes. But we discuss later on the difference in terms of scale and complexity, and what this representation have, or what the mesh region have more in terms of advantages. So in dimension 3, this is the set of primitive we support: ball, capsule shape, cuboid. So if you really think about it, they're all linear base cells, and then you have also quadratic base primitives. And in terms of transformation, as I told you, for CGS, constructive solid geometry, usually you want to preserve that physical fidelity. So you restrict yourself to a set of, geometric transformation, which are pretty much affine transformation. So essentially you want to, the set of transformation which preserve orientation as well as isometry, pretty much, except scale and such. But you pretty much want to not deform your object and remain, start with a rigid object and at the end stay with, get a rigid object. So in this case, we support translation, scale, rotation, and geometric transform, where you can actually specify an affine transform. So before I start to show some example on what you can actually achieve with this new object and in terms of representation, I want to slightly look at all the modeling and representation scheme we currently have, right? And that will kind of help you or understand why we introduced this and what's the difference with what already exists in the system. So in terms of representation scheme, we have, implicit region. which allow you to implicitly represent a set of points. So if you have a set of points you can describe with predicate, you use implicit regions. Like a ball, you know that it's x squared plus y squared less than 1, for example, the unit ball. So you just use that representation. So for surface mesh modeling, we have boundary mesh. And in this case, I'm just restricting myself to solid modeling for the time being. So you have boundary mesh, and we hope in the future to have spline or NURBS. So you can actually do that surface modeling in the language. And in this coming version, we're introducing CSG region. That is for constructive solid geometry. And for primitive instantiation, we have all the basic object coming from graphics, ball, tetrahedron, polyhedron, and such. Right? So the language or our geometry framework support a large collection of representation and scheme for construction of regions. But we go a little bit further, right? And in terms of geometric modeling, which is a little bit bigger, we have Boolean region, transform region, right? And what is important here for you to understand is that each object, right, implicit region or boundary region, provide you an easy way to express or model a set of points in Rn. But also that description will definitely affect the analytic part or the computational part later on down the road. So if you have an implicit region, right, which is described by a polynomial of a certain degree and such, right? And that implicit region can represent as a boundary mesh or as a CSG tree. Just the computation of the measure, or let's suppose even it's a 3D object, or volume will be affected by your representations. Right? On my earlier talk, I was describing one of the key things we try to push in every release, which is the usability. So we try to make sure that when you use the function region, measure, or volume, it can handle all those representations and do the computation behind the scene appropriately, independently of how you present that set of points, right? And what we actually try to achieve, I mean, as you can imagine, it's actually hard because if you have an implicit representation, even of a 3D object, and the volume is a multiple integral, maybe we don't even have a way to represent to find that closed form with special function we have, right? So what we try to do is to actually add to all the function we have working precision. So when we cannot find it, or we know we cannot actually represent that output with a closed form, if you give us exact input, we fall back to numerical computations, and we highly rely on our discretization or mesh mechanism to actually approximate your set and do the computation. Right? So it's one thing you have to keep in mind, and we kind of try to propagate that to the system. So you have the flexibility to model your object using all these different representations, and we try to automate the computation and rely to the discretization as a fallback for that, right? And and I heard several questions why people were actually asking, what's the difference between Boolean region and the CSG region we have now? And the key point is that in terms of modeling as well as property, right? So the Boolean region is that the general, geometric modeling object, which doesn't have any restrictions, where the CSG region is restricted to a finite set of primitive and regularized operation. So you know that when you intersect object, you get a solid or an empty set. Right? And it's actually what gives the power to that object to work faster for better auto visualization and such. So this kind of hopefully gives you a view of the different representation scheme and what we are doing and how we are building the different model and such. Right. And we hope that in the future, as we jump to, for example, sweeping, representation or technique, we introduce those objects, or parameterized or feature-based modeling will introduce, way to actually, handle it in the system. Okay. So now let's actually try to build something concretely and see, the power of this new object and representation. So this is just a model provided by Alec. It just is, simple shaft bracket. Can you actually model this with the new CSG region we have? So, so if you just look at it the simple way, you see that is, essentially cylinder plus, 2 cube pretty much. Let's, assume that they are linear. So I'm not going to do the curve and such for the time being. So what you do essentially, you take the cylinder and then you join the 2 cube, but it is usually addition and removal of material if you want to model an object in this case. So you have that base object there, and then the next is actually what are you going to remove. So in this case, you see, if you really look at the picture, you probably have to remove a cylinder in between and on top. So if I do that and I do the difference, I get the object here. And what you notice, for example, what you notice for this object, that it's auto-visualized compared to Boolean region and such, because here we actually know that it's a solid object. We know already property, and it was one of the, one of the key features for the constructive solid geometry. The validation is already there, so we don't need to compute and see if the object is empty, if it have lower dimension and such. And so it's what actually facilitates, this auto-visualization, which we do actually directly on the graphic card through GP, shader language and render you that, and we can easily rotate it and it behave like, pretty much any graphic primitive with wide performance and such. So let's look at another model. Actually, most of this model, we actually, pick them from, a repository for CAD from engineering. So let's try to actually see if we can actually build also this one, which is a array support. So first you build the base. In this case, I do a union of cuboid. And from that, I will probably extract, the cylinder and the axis. And if I run that, I get that object. Right? So at the end, it's just that, base idea of, building first the base object you have, right? Based on addition, and then know what you have to remove from it. So you get the actual object, and you can take that object and actually compute the volume and manipulate it. As I also pointed out earlier, also, right, that computational side is essentially, conversion to Boolean region. So using those Boolean property, Boolean algebra of the object. Okay, so let's look at another little bit more complicated object, which is a pipe bracket in this case. So I first build, one of the positions. So I will go a little bit further here. When you get really used to it, the operations are really basic, and it's just the set of objects you are manipulating. So these are the corner. We build the difference, the union of the base object, and the end, you get the bracket. So pretty much most of, the basic object you can think about, right? As you can simulate in a CAD, you can actually build it here, right? And just to show you that it's a little, there's a little bit more than that. You can actually take something a little bit more difficult, like this universal join, right? So if you really look at it, it's a set of, you can think about the cylinder plus ball plus, a smaller cylinder, and then you have different holes. So essentially, we just play between, adding cylinder and removing cylinders. So we have the cylinder here. We build the first part. build the part you will negate, and then you first get the first York module of it. So you have it here. And then all you have to do is pretty much just duplicate the same process, plus or minus rotating the base object. And then at the end, you have that model. And this is essentially a pure mathematical expression, right? And as I said before, that conciseness of that, solid modeling and, the ability to actually just take that original object and just change it, like you see here, translate and rotate and nest them is actually extremely powerful. And is where is that part you cannot really do with Boolean region, and Boolean region actually evaluates. So you are losing, the information is lost during that process, right? Where in this case, which I will not do right now due to the time, but you can essentially take it, put easily a parameter T here and put it in a manipulate and control maybe the size of the ball or the rotation of this object, right? So you can just control the parameterization and modify it quite easily. So it's actually a really powerful language in terms of modeling. And it's mapped really nicely with the Wolfram language, right? Because we have our expression are pretty much tree and such. And actually, it's come back to my second, my next slide, right? Is essential is that, right? The CSG tree is essentially a tree, right? Like we saw at the beginning. So you can actually easily represent it with our tree expression, which was introduced in, I think in version 12. And you can easily manipulate it. So this is a standard example, right, of people who play with CSG. So you have a circle and then you remove the cylinders. So this is a sample function CSG tree. We generate the tree and just show you the tree of the original object. Right? So it's precise, concise, and you see actually the flow of how you constructed the object. And you can give this information to someone else in your team, which continue the modeling and can take it and maybe change one of the object, add and manipulate the expression. So you keep track of actually your design intent and the process of your design. As you want, as you wish. And so this is just another example of how you can just pretty much just manipulate it in the language. In this case, I just take that resulting tree and then use our tree extract to just take the second part of that and just look at it or convert to it. So if you disregard this message, just a prototype case. So here tree expression just regenerate the CSG tree from the second level of your tree. Right? So from the original tree here, I can take this second level or manipulate it or insert new object. So you have that flexibility that you jump back to the Wolfram language and manipulate, that model, with just that tree, structure. Or in this case, you can just do tree leaf and see all the basic primitives you have in your model. So the CSG, the computer geometry representation actually nicely integrate with the language, which is actually pretty nice and makes stuff actually simpler to play with. Okay, so as we push, this is a kind of a subsystem, and hopefully a big subsystem will keep improving in every release. So what we'll try first to do probably in the next release will be to introduce a CSG tree, which will be the base data structure, be pretty much available to everyone, and you can actually take it and use it in the compiler. So what we try to do in long term is that you can actually take data structure we use behind the scene in geometry and actually also use the compiler and get your code or generate code, which will be extremely powerful. There'll be more functionality to manipulate those expressions. So extract, delete, insert tree, discover which part you have. But also will, in earlier talk, I presented, reconstruction. We'll try also to kind of integrate it to the whole pipeline. One common function will probably, region approximate, where you will take a mesh and try to find what's the best approximation using, a CSG region. which is a, kind of a quite interesting problem. And we believe that we know how to do that. And then you can get actually an approximation of your mesh region from a CSG tree. And obviously we have the, the process back where you can just discretize the CSG tree and get your mesh region. So we keep on, that workflow always is present. Okay, so that's pretty much what I want to show with the time we have. So we have a whole framework for computational geometry, which fit very well with the language and the geometry computation we have. And I hope you will use it to model object, manipulate object. And that's pretty much it. So I will try to answer a few questions now. And if there's even more, join us to our office hour, which will be at 1 p.m. So in 30 minutes. This is 1 p.m. Central Time. And the whole team also have a graph and network tour office hour just after that. Okay, so I will try to look at a few questions here. So one question is, what are the output of the CSG region? So are the region object, or do they maintain the tree structure, the primitive involved in the construction? Yes, they actually region object, and they maintain the tree structure as I showed earlier. So let me hopefully go back there. Well, so let's take, well, for example, this one I do input form, right? So it's exactly the tree structure, right? Which is encapsulated by our tree expression form, right? And it's actually why the powerful of actually be able to do, procedural modeling come into place. So you can just take this expression, manipulate it. So it's both a region and also a, an expression which maintain the tree structure. So another question from Dave, from mechanical object, they would typically be filled at 90-degree angle to smooth out the sharp corner, right? How will you recommend adding fillet? Yes. So at this time, we, as you saw, the object we have, I mean, the basic primitive we have, right? Several of them are linear and other ones are essentially, volume of degree quadratic form. So you can actually essentially take those, like a ball, and use it to fillet or to smooth the angle in your object, right? But we hope in future version to have actually more primitive as we extend, the base primitive for the CGS region to actually, allow you to do that quite easily. Another question from Dave de Bruta. How about the function to erode a CGS object to smooth out the sharp, yes, to smooth out the sharp edges? Yes, so that's also in plan. So we will kind of consider all those set of operation or object, right? So those also include sweep, operation and such. So to facilitate, more of the construction. So, if you have more suggestions, feel free to put them in the chat or send them to me and such, and we'll be happy to actually add those features coming from your specific application and use, right? Because the main goal here is to actually make it powerful enough to model your, any object you want. Okay, so well, it's pretty much time, and please, feel free to stop by our, office hour at 1 in 30 minutes if you have more questions. And, thank you for coming.